All right, my friends, one more little video about the polar coordinate system, and you should do just fine with the problem set. So this is the polar coordinate system. Continued. Okay, let's look at example 4. Let's have you graph. Actually, we'll make this part A of example 4. Graph the polar equation r equals 3. Okay, this would be something super easy to do with just hand drawing some polar graph paper. I will make sure though that everybody has access to this polar graph paper that I like real well. It's kind of nice just to have it pre-done, and then you could just paste it into your notes. A note for this graph before we get started, since they didn't say anything about theta, that means theta is what's called unrestricted. So theta gets to do whatever it wants. R is just fixed at being 3. So if you think about, what if theta is 0? Well, R would be 3. And what if theta is pi over 12? Well, R would be 3. And so theta gets to do whatever it wants. It's just your R value that's locked in at 3. So if you start plotting all of the infinitely many points that have an R value of 3, pretty quickly you'll find yourself drawing a circle centered at the origin or the pole with a radius of 3, which is funny because that is exactly what that says, R equals 3. So I'll kind of show with highlighter where the actual graph would be. And all the infinitely many points would blend together and form this perfect curve of a circle. There we go. And just for the record, you could have done that very easily on hand-drawn polar plane. Very easily. Okay. All right, my friends. For part B, let's have you write the equation of this circle in what's called rectangular form. Okay, so to be clear as to what they're asking you, they're basically asking you if this wasn't a polar plane, if this was an XY plane, then what would the equation of this circle be if you were plotting it in an XY plane? And there are lots of ways to get this answer. There's just look at the picture, which I'm about to do, and then there's also an algebraic way to go about it. So depending on your experience with circles, you could just treat this circle as if it's an ellipse centered at 0, 0, and you could say, oh, okay, well the equation is x squared over 3 squared plus y squared over 3 squared equals 1. You could also multiply both sides by 9 and get what many people also would say the answer is. These are both perfectly great answers. There we go. I hope that makes sense. But really this question was meant to kind of springboard the idea of converting from polar form into rectangular form. And there's a way to do this algebraically, and you don't always want to have to be doing it graphically because it can be pretty tough. So let's talk about that. So converting between rectangular in polar form. There will be 4 little identities that you should memorize, but they're the kind of thing that if you were to draw the simple little picture here, you could actually teach yourself the identities in a pinch. So I've drawn a plane here, and if I was to ask you, hey, quick, is this a polar plane or is this an XY plane? I kind of hope that with the information that I've put on it, you would say, I don't know, because I really haven't put enough information on it to determine which type it would be. It could easily be a polar plane or a rectangular plane. And as a matter of fact, we're going to use it for both. So let's say I put a point on this plane and I say, okay, this is a polar plane. So this is the polar axis, for example. So if this is a point in a polar plane, it would have a coordinates pair that looks like r theta. And what would the significance of r be? Well, r would be the distance from the pole out to this point. And what would the significance of theta be? Well, it would be the angle that you rotated counterclockwise from the polar axis. Well then, what if I was to say, okay, well now it's an XY plane. So this exact same point, instead of having coordinates of the form r theta, it would have coordinates of the point of the form xy. And what would the significance of x be? Well, x would be how far you would have moved along the x-axis to get right underneath that point right there. And the y value would be how far you moved vertically to get to that point. And so if you look at this simple picture where all we did was look at the same point, but we looked at it as a polar point and we looked at it as a rectangular point, then you look at this little right triangle and you'll have all sorts of little identities that you can get from it. So for example, the cosine function. If I asked you what's the cosine of theta, you could just say, well, it's adjacent over hypotenuse, or x over r. And notice this expression has theta and r in it, which is polar, and then it also has x in it, which is rectangular, which means it's a way to kind of maneuver from one form to the other. Similarly, sine of theta is opposite over hypotenuse, or y over r. Tangent of theta, opposite over adjacent, or y over x. And last, good old-fashioned Pythagorean theorem would say x squared plus y squared equals r squared. There you go. And this is really your toolkit. Now, the cosine identity here, sometimes it's going to be helpful to have this kind of split up where you have all the polar side on one, all the polar stuff on one side of the equation and all the rectangular stuff on the other. And that could be accomplished just by multiplying both sides of this expression by r. So this expression, sometimes you'll prefer to have it written as x equals r cosine theta. And then similarly, the sine expression, if you multiply both sides by r on that, you'd have an alternative version of that one as well. Okay, my friends, this is your memorize this cloud. Respect the cloud. Memorize your identities. You'll be so glad. Okay. Also, something that's going to be coming in your notes, in your homework, and on your test when it comes. Go ahead, go for it.
Okay, sorry.
No, it's okay. Okay. All right, my friends. So something that's going to come in handy is the double angle identities for sine and cosine. Sine only has one. Take a second and see if you can recall what that is. It is 2 times sine of x times the cosine of x. Good job if you remember that, by the way. Cosine of 2x has 3 because the first one that you would get has trig functions squared, so the other two are just Pythagorean swaps on these. So you could swap 1 minus sine squared out for the cosine squared. You'd end up with that after you combine like terms. You could also swap out 1 minus cosine squared out for the sine squared up here, and you'd end up with let's see, minus 1. There we go. Okay. Okay, so before we do the last examples, study everything in this toolkit, and then also re-study your double angle identities here for sine and cosine. All right, my friends, example 5. Directions, convert each polar equation into rectangular form. Okay, part A. Let's just kind of recycle here. Let's give you r equals 3. Okay, now you know very well what the answer is going to be. We've already talked about this one. It's a graph of a circle, and then we were able to get the equation just by looking at the picture. What I'd really like for you, though, is to not always be dependent on having to graph it first. So instead, what I'd like for you to be able to do is figure out a way to convert it algebraically. So, and with that, you have a lot of choices that you could make here. And I would love for you to be able to choose the most elegant method for getting through this problem. So with that said, notice that this equation has r mentioned, but it does not have theta mentioned at all. So if you look at your toolkit for converting between rectangular and polar, almost every identity but one has theta in it. So what that does is it kind of pigeonholes you a little bit into hopefully knowing that it's this last identity that we're going to reach for. Notice this identity has r squared in it, so I'm actually going to start off by squaring both sides of our equation. So if r is 3, that means r squared would have to equal 9. And then you're trying to get out of polar and into rectangular, so that means bye-bye r and theta, hello x and y. So you could replace r squared with x squared plus y squared. And then you know you're done, because this is the answer that we got when we did it graphically anyway. All right, part B. Let's think about what if I gave you theta equals pi over 4. Okay, so r is unrestricted. Your angle is locked in at being pi over 4. So let's think really quick for all of your identities, which one makes sense? Well, all of the identities have r in them except one, except the tangent one right here. So tangent of theta equals y over x is going to be the tool to reach for. So I'm just going to write that. Tangent of theta is y over x. And then you can put pi over 4 in for tangent. For theta, that is. Evaluate the tangent of pi over 4. It would be root 2 over 2 divided by itself, which would be 1. At this point, you have accomplished what they asked you to accomplish. However, don't be surprised if, with a problem like this, if you check your answer in the back, if they multiplied both sides by x. Now let's talk about why it makes so much sense to multiply both sides by x from this answer to this one. If you think graphically for a second, if I asked you to graph in the polar plane all the points that have an angle of pi over 4, where r is unrestricted, here are a bunch of points that have, so here are all sorts of positive r values that have an angle of pi over 4, and here are some negative r values that have an angle of pi over 4. So I hope it would make sense. You would get this line graph here. And then by writing your equation instead of as 1 equals y over x, as y equals x, it really should kind of make sense with your graphical reasoning. It's this, a line graph, a y-intercept of 0 and a slope of up 1 over 1. All right, my friends. So let's do one more that's about this level, and then we'll do a challenge problem. So part C, let's say I give you theta equals 5 pi over 3. Same thing, I didn't mention r, so you wouldn't want to reach for any of the identities that have r in them. So you'd reach for the tangent identity again. So tangent of 5 pi over 3 would equal y over x. Evaluating the tangent of 5 pi over 3, you could just imagine the unit circle. Here's 5 pi over 3. The coordinates there would be 1/2 and negative root 3 over 2. So the tangent would be the y coordinate over the x coordinate, which if you think about it, that is exactly what that identity is saying. Flip and multiply, cancel the 2's, you'd end up with negative root 3. Multiply both sides by x. There we go. And what about this answer makes so much sense? If I was asked you to graph this, you'd graph a line with a y-intercept at 0 and a slope of down 1.7 and over 1. And that should make a ton of sense, because if I ask you to graph theta equals 5 pi over 3, your r value is unrestricted. It could be any positive r value or any negative r value, just locked in with an angle of 5 pi over 3. All right, I hope that makes so much sense. Okay, part D. All right, here's the challenge problem, my friends. Let's see how it goes. R equals 3 times the cosine of 2 theta. Super good time to pause the video and see what you'll do with that. So when asked what makes this problem challenging, a lot of people pretty quickly can tell you the 2. Because when you look in your toolkit, you don't see any double angles. You just see regular old single theta inside each one. So that's why I mentioned the double angle formulas that we've got. So you're going to need to expand this using the double angle formula, which will allow you to use the identities in your toolkit. So getting started there, I'm going to use this one, even though there are 2 other perfectly good options that you could have used. Next, since I'm just going to make a note here, cosine theta is equal to x over r. So cosine squared theta would be x over r squared. Similarly, sine of theta is equal to y over r. So sine squared theta would be like y over r squared. Okay. Next, I'm going to simplify inside here. So I'd have r equals 3 times the quantity, x squared minus y squared all over r squared. Okay. Let's stop and kind of take stock of where we're at. We're supposed to get rid of all r's and thetas. I did get rid of theta at this point, but I still have some r values to get rid of before I'm done. So r squared can be swapped out for r squared can be swapped out for x squared plus y squared. So that one's taken care of. And then the single r value, I would swap it out for plus or minus square root of x squared plus y squared. Technically, you're done at this point. They asked you to write this in rectangular form. We got rid of all r and theta. We introduced all x and y values. And this example definitely shows that some things you're better off with in polar form. This one, when we translated it into rectangular form, it's a lot. It's a busy thing, and it would be hard to work with. So we would be better off in this case with the polar form. So I do want to make note, though, that commonly, since you've got this x squared plus y squared and then the same thing underneath the square root, commonly you'll see where they multiplied both sides of the equation by x squared plus y squared, in which case they'd have something like that. And then this piece right here, if you think about this, this is like x squared plus y squared, to the 1/2, and this is to the first. So just want to make sure everybody would be okay if you saw something written as plus or minus x squared plus y squared to the 3/2 equals 3 times x squared minus y squared. There we go. And I don't especially like this answer better than the one that we had before. I just wanted to mention that they're equivalent. All right, my friends, last example, example 6. The directions are to convert each equation from rectangular to polar form. Okay, I think we'll just do one of these. So x squared plus y squared minus 2y equals 0. Super good time to pause the video and see how it goes for you without my help. All right, so to go about this, I would notice the x squared plus y squared right there, begging me to swap it out for r squared. The y, I would use the identity since sine of theta is y over r. Y is the same as r times sine theta. So I'm going to put r sine theta in for the y value there. There you go. And at this point, you're pretty much done. When you check your answer in the back, this is likely not what it will look like. So just a couple steps to show you what the answer in the back would look like. They'd probably multiply that second piece out. They would also probably add the 2r sine theta over to the other side. And then, and this is something that in the past has been a no-no, but because of the way the polar plane works, it's going to be okay here. In the past, it's been a big no-no to divide both sides by a variable expression because you would have lost solutions. Here, it is going to be okay, and here's why. The solutions you would have lost would have been where r equals 0, which is basically the pole or the origin, which if you think about a point that's on the pole or the origin, this equation would generate that same thing as is, even without the extra r there, because if theta was 0, it would cause your r value to be 0. So you actually didn't miss out on anything by dividing that r over. All right, my friends, I hope this is helpful to you. Take care, everybody.